Good afternoon, everyone. Today we'll be presenting on the cellular and biomechanical impacts of differential loading of the intervertebral disc. My name is Arnold.
I'm Matilda.
I'm Robert.
So a bit of an introduction. First of all, the intervertebral disc main function is to provide weight-bearing capacity and spinal flexibility at the same time. So there are three parts in the intervertebral disc: the inner layer or the nucleus pulposus, the annulus fibrosus, as well as the cartilaginous end plates. So back pain linked to degenerative disc disease is a serious health problem, with about 12 to 35% of people having back pain and increasing severity of degenerative disc disease with age.
Okay, so we can jump right into compression. So compressive loads, there are two types. There is static loads and as well as dynamic loads, which are sort of loads that have time scales. So they'll load on and they'll load off over time. The general consensus is that compression has a significant effect on the nutrient levels inside the IVD. So if I could turn your attention to the top figure with all the colors, this is a fine element analysis of a computationally modeled intervertebral disc. So the top one is oxygen, the middle one is a map of lactate inside the intervertebral disc, and the bottom one is a pH scale. And what you can see is that once these are compared to a disc without any sort of compression on it whatsoever, you get a decrease in the amounts of oxygen inside the intervertebral disc and an increase in lactate production, which is sort of like the opposite of what you want inside a healthy living cell. What's nice to know, or what's interesting to note, is that under dynamic compression, you actually see the opposite effects inside these computationally modeled discs, and you get an increase in oxygen production and a decrease in lactate production. But this is not something that's universally true. There also has to do like timescales with it and magnitudes, because in other studies, dynamic loads have been found to be sort of degenerative, and they upregulate collagenase, aggrecanase, and stromolysin, which are all enzymes that break down the collagen and vital proteins that our intervertebral disc is made up of. To cap things off, there are also a bunch of in vivo models done in animals, but the general consensus is that you can show that static loads really do have a harm on the intervertebral disc. And what you can see here on the bottom figure is an example of the histological analysis of multiple samples. So a higher graph means that it's been more degenerated, or it's had seen a greater degenerative effect. Group A being just a static load, Group B being a static load combined with rest, and Group C being a static load combined with distraction loads, which are just differently directed loads, so they have different directions. And Group D is a control. But yeah, main takeaway is that static loads really do harm the intervertebral disc.
So I'll be presenting on the shear force. So the effects of shear are actually less understood than the effects of compression forces on IVD. So while compression forces typically have a larger magnitude to failure that compared to the shear forces spinal structures are actually weaker than the compression force spinal structures. So shear force can have a variety of effects on the IVD. So in a mice model, it has been shown to lead to greater IVD degeneration with decreased demarcation of MP from AF, complete loss of the MP, as well as depletion of the proteoglycan layer. In the human spinal disc, it has also been shown to have different levels of effects depending on the direction of the shear force. So there was work to failure, higher in the lateral than the posterior and antero. However, the shear force leading to failure was higher in the posterior antero compared to the lateral direction. And finally, the shear force has been implicated with a key spinal disc remodeling signaling pathway with AP1 as its final product. So AP1's main function is to degrade the proteasome family of the extracellular matrix, which remodels the gel-like substance in the spinal disc. So other studies have proposed to selectively inhibit this signaling pathway as a means to treat degenerative disc disease.
Torsion is another major loading environment for the intervertebral disc. The intervertebral disc can be modeled as a cylindrical shaft, which is subject to torsions about its longitudinal axis. So these torsions are in normal everyday motions like twisting and turning of the head, and many athletic activities involve larger spinal torsions. Low angle, low magnitude torsions may be beneficial, particularly to the cells of the nucleus pulposus, increasing cell viability and metabolic rates. However, high angle, high magnitude torsions are associated not only with IVD injury, but with an upregulation in catabolic proteins and loss of proteoglycans. Both of these processes may contribute to and are observed in degenerative intravertebral discs. Due to the hydrated contents of the nucleus pulposus and its lamellar container, the cells of the nucleus pulposus and the annulus fibrosus are subjected to pressurization under compressive loading. The role of pressurization is particularly important to the phenotype of the notochordal cells in the nucleus pulposus. These are large, vacuolated, immature cells that decrease in number with aging and degeneration of the IVD. Pressurization of the IVD correlates with the maturation of these cells to a phenotype that is less rich in proteoglycans. However, small magnitudes of hydrostatic pressurization have also been observed to increase expression of aggrecan and collagen II, which are anabolic matrix proteins found in healthy IVDs. Pressurization thus remains a complex IVD loading environment, and the magnitude and frequency of the loading environment may be critical to its impact.
All right. Yeah, so main takeaways are that various forms of loading and different types can result in sort of degradation or downregulations of these vital nutrients and proteins of which the IVD might need or is composed of. But as we can see, there are different magnitudes and time scales that show that different loads can also be regenerative. So looking into the future, we want to see what other forms of research can come about. And this is likely lying in either human spine cells derived from like pluripotent cells or just computational modeling like COMSOL.